Yeah, thanks. There's some mechanical noise out there. I need to tell the chair to report it. So this is really the last day of prepared material. Monday, we're going to sort of explore things that you guys are interested in diving deeper into. So this one has a few conversions in it that are related to the homework. I was telling you about it a couple days ago. And so we'll go through this. We've talked at this point about combustion sources of energy, and we use that many times to make electricity, but also to drive our vehicles. We've talked about nuclear particles, how to measure it. You did a radiation lab. How'd the Wednesday lab go? Was it good? Okay. And then we talked about nuclear power last time. But again, we're getting to using all of these technologies to make electricity. And now let's talk about how we store electricity and then other ways to make electricity. So we have different sources of generating electricity and the different ways of storing it. And so, of course, we have batteries. That's what the whole redox reaction, and we were talking about non-equilibrium systems. We got into redox reactions. That's what we're using for batteries. We'll see in this set of notes, the flow cells. So batteries with a flow of reactants instead of just static, like a battery with the reactants inside and then it goes dead. So, and electromagnetism, we can use magnets and electricity and their interactions to store electricity. So we can use motors that use magnets and coils to spin things and make mechanical energy, and then we can put a generator on that and get electricity back. And so there'll be flywheel electrical storage. So we'll see a lot of interesting things today. And then photovoltaics, where we get into turning light directly into electricity. And then storage, there's this balancing act between short-term storage and long-term storage. So we really have this wide range of technologies that are focused on particular problems. So it's when you say, how do we store electricity? Well, you've got a purpose for storing electricity. And there's that purpose to store electricity so you can get it out quickly and have a lot of current, maybe to start a vehicle or to drive, a drivetrain. So there you need a huge amount of current. So you need a lot of a voltage and current to give you current through these coils that give you a lot of torque. Okay. Or if the grids for some reason is generating more electricity than the residents and the buildings need, can we slow that huge electrical train down by pumping, say, water uphill and storing electricity or energy and potential energy or using gravity? So there's lots of things that we can do. This idea of short-term and long-term storage has to do with impedance. And so if you're impeding something, you're slowing it down. And most of the time with electricity, you're thinking of resistance. Like you have a resistor and the current's flowing through a resistor, and that resistor slows things down. But pulling on a source is also how we measure, how we call impedance. We're pulling on the source, and if the reaction rate is too slow, we can actually pull too hard, and the voltage will drop. And so think about a battery. If you short circuit a battery, it's not going to maintain its voltage. It's going to drop. The reaction rates are not going fast enough, and therefore it's not able to maintain that cell potential. So every source of electricity has an impedance value, how fast you can pull current out of that source. And then we don't want to have lossy storage. So if you put something in a battery and its barriers are such that it leaks, then it's going to lose some of that electrical potential. If we store water uphill in terms of hydroelectric and we have evaporation, again, that's a real simple visual concept that you can see. I mean, the water level at the top reservoir is dropping because of the sun, not because we're getting that energy out that we put into it. So that would be a lossy storage medium. And so I was looking at lossy. I couldn't see that was ever used anywhere. And so that's what we've always called it in my training, in academia, that you would store something, and if it was lossy storage, it was crummy. I mean, you basically paid for what you stored there, and now it's gone. So I went ahead and looked it up, and yes, that's my definition: a transfer process or storage medium that leaks or loses material or information. Urban Dictionary says it's someone who's a pothead. So, so anyway, that's my definition. If you store something in something that leaks, your pouch has a hole in it, that's lossy. So what we've done here is here's our regular conversion efficiency diagram, and we've added this last one here. So this is new, to where we can take mechanical energy, and let's say we have the electrical grid, like I said, is going full power, and then a cold front moves in, and then those people don't need their AC on, and then they turn them off. Well, it's almost like a water hammer. A water hammer is you're flowing water, and then you turn the water off abruptly. Well, all that momentum of that water is still coming. And in houses, they'll put a little vertical pipe with a cap on it. So the water's coming in, it goes to the faucet. Let me just draw this. Water's coming in, and it's going to the faucet. Okay, so you got the little faucet on here. And it's flowing out. And if you turn that water off abruptly, it'll rattle the pipes. Like sometimes houses, you'll turn the water off and you hear boom, 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 boom. What is that? Well, that's the momentum of the water rattling the pipes, especially if it's going around a lot of 90-degree turns. So it hits that 90-degree turn, it stops abruptly, but that momentum needs to be stopped, and so the pipes will rattle. So they put this little tube, this vertical tube up here, and they cap it off. Now, they put this whole water line together when it's empty, and so there's air in that tube, and so it's like a spring. And so you turn off the water abruptly, and that air pocket gets compressed, and then it comes back down, and that keeps your pipes from water rattling. Okay, and that's sort of a damper for that water hammer. Same thing with electricity. If we're pulling utility-sized current through these power lines, and a cold front comes in, you shut off all of your AC units, then what do you do with that demand? All of that electricity flowing through. They're starting to put things on here like this compressed air or gravity, where you've got the mechanical spinning of the power plant generating electricity, and the electrical demand goes down. Then they take that and pump air down into a reservoir or something, or into a cylinder, some large space. And so that's acting like this top pipe. Okay. And what it does is it levels the electrical pressure, if you will, the load. And so load leveling is really key. Now you can do that with, let's say instead of having this coal-fired power plant or nuclear power plant, you have hydroelectric, and that's making, spinning a mechanical generator. And once again, the electrical demand drops, then you can spin that mechanical, instead of a generator, a pump, and you can pump it back up. So water's going over the dam, spinning this mechanical generator. You can switch over and clutch into a pump that pumps water uphill and stores it at a higher spot. Then later, when demand goes up, then you can pull some of that water down off the hill. So that's this. So this area here is sort of a load leveling device, and it's huge. So let's look at our electrical energy flow. We've done this previously, but I was showing you how it was the 2002 numbers, and we had net primary use in 2002 of 115 exajoules per year. We looked at the efficiency of the electrical grid was about 31%. We said there was a lot of room for improvement. The transportation was about 20%. Industrial and residential were pretty good, close to 80%. Well, in 2019, I found the figure for 2019. The electrical grid improved. We got up to 34%. The efficiency of homes and commercial dropped a bit. And then transportation improved a small amount. Now that's 2019. Look what happened. So we were at 100 quads, which again, a quad is about close to an exajoule, like 5% more than an exajoule. Okay, so that's about 105 exajoules per year for 2019, and then COVID hit. So this is kind of interesting. We dropped to 92 milliquads. So that's an absolutely mind-boggling amount of energy that changed. I mean, we're talking about 10 to the 18 joules. That's a lot of energy. It didn't change our efficiencies that much, though. So, but to think about that, that's an enormous amount of energy. But still, it didn't change, but 8%, 8 to 9%. In a global pandemic, and all of the things that we changed. We didn't drive as much. We didn't eat as much. We did use a lot more electricity at home. You can see the residential numbers here. So look, this is 745 exajoules roughly in 2020, and it was Oh no, it did go down. I was thinking that it went up because of Zoom and sitting around the house and watching Netflix. Yeah. But yeah, it dropped, and so did the commercial. Let's see, it went down. So pretty much everything went down. So the efficiency went up a bit again. So the electrical efficiency went up a bit. And so then I was talking about this load leveling, this idea, and so we can do this every day. There's some sort of load leveling that needs to occur. And so what we'll do is we'll take these large power plants, this coal, nuclear, hydroelectric, and that will be the base electrical generation. And the real efficiency gains have come from natural gas turbines to do the load leveling, because this is essentially what we looked at with the combustion sources. It's just a jet engine, that runs on methane and spins a generator. And so you can start an airplane engine, you can turn it off a lot faster than you can start a coal-fired power plant or a nuclear power plant or a hydroelectric. And so we can turn that off when it's midnight and people aren't using a lot of electricity, and then we can turn it on when people go to work and all of the buildings are full and the ACs are running full speed. And so we can use that natural gas turbine to level out this electrical demand. And if we were trying to level with say coal-fired power plants, the demand would drop, and then there'd be a huge lag in turning down the coal-fired power plant output. And so that's the part right here. This electricity just gets thrown away in some form. I don't exactly know how maybe they just unclutch the generator, and yet they're still producing steam. And so they're burning the fossil fuels and they're producing steam, but they're not generating the electricity because demand has dropped. Whereas on the gas turbine, they can turn that off fairly quickly, and then they're not burning any more natural gas. Like this can be shut off a lot faster and turned on a lot faster. So let's talk about our consumption. So the average power of a house, Entergy, Texas, they sort of give an average customer of 1,000 kilowatt hours a month. Okay. And so that's that power for your house at 1.3 kilowatts, that would be average. That's not bad for a generator. I mean, you can buy a 2,000 watt generator, 3,000 watt generator for a fairly reasonable price as a backup. And you can find these generators for your whole house. Typically, they get up to around 7,000 kilowatts for a house whole generator, so that you can handle what they call the inrush current. Whenever the air kicks on or whenever the freezer kicks on, there's to turn those compressors, there's a quick burst of current to get those compressors started, and that will trip the breaker on a smaller generator, but you need a little bit faster one. So what is the amperage for that? Well, it's coming in about 11 or 12 amps, which is the current that's coming into your house. But that would be the average over the month, every day. At night, much lower. Middle of the day, a lot higher. Okay. Let's talk about the spectrum of energy storage. So this balance between needing that power quickly versus needing it over time, over a large amount of time. And then how much energy can you store in there? Like a small battery that stores just a few joules to a large battery that stores a lot of joules to something like a reservoir that stores an enormous amount of power, energy. And so this is what I was talking about. If you're using this hydroelectric dam to generate electricity and then all of a sudden demand drops, you can use some of that electricity to pump this water uphill to this upper reservoir. This can be lossy, okay, so you can have evaporation. And so what you'll see for these reservoirs is sometimes they'll put these little beads, and they'll cover the whole thing with plastic beads that essentially take the surface area and shrink it down to just the space between the beads. And so that dramatically drops the evaporation rate. You don't have to be next to a body of water. So you could build 2 reservoirs out in the middle of nowhere and just hook it to the electrical grid. And so if demand drops, then you can pump that water uphill. And then if demand peaks or starts to come back up, then you can use this as a hydroelectric generator. And so this would be, again, large, what we say, commodity storage. So this would be a load leveling technique. Now, if you need rapid response, okay, like all of a sudden my laptop, something happens and the power goes out, I need an uninterruptible power supply. I need something that can kick on instantly and generate a fair amount of power. This is an interesting one. This is mechanical energy storage. These are called flywheel storage devices. I really love this flywheel idea. So you've got this device that's spinning inside, and you put electricity in it. There's a motor, okay, and it spins up this heavy object and stores energy in its mechanical motion, okay. And then when there's demand, you clutch into that and you spin a generator, and so the mechanical motion turns a generator, and you pull the electricity back out. So you're just storing electricity in momentum. I could see these things being in the basements of homes. And so what you would do is you would have solar cells on your roof or out next to your house, and you would store up the excess electricity in this flywheel storage, and then at nighttime you could use the flywheel storage. And so this is, and guess what? There's no electrodes to degrade. There's no chemicals to buy or whatever. So it's going to last. This has one of the best lifetimes in some of these fast, rapid response storage media. So what does this mean, power quality? Well, power quality means that beautiful sine wave that we want from our AC current. And we don't want it dipping down. We also want, that voltage to be maintained at 120 or 240. And so you can have this be between, say, a dirty power supply and your house. And this will make your house have a beautiful sine wave. And this can be a little bit messy. Okay, it's pushing that generator when it can, and it's fine. It's good for cleaning up that signal. And so if you have electrical instruments that you want to maintain and make sure that they're noise free, like in a chemistry lab with instrumental analysis equipment, they can put these in as uninterruptible power supplies and also what they call power conditioning. So it makes a real nice, pretty, noise-free power source for all of your instrumentation. And that's why they have this one with NASA on it. Okay, so this is flywheel storage for some satellite or something. I don't exactly know what they've got going on there, but they're probably using that for power conditioning and maybe some UPS activity. Now this sort of shows that I talked about commodity storage. That's where you're storing the electricity for long periods of time, like 10 hours. Okay. You can store a lot of electricity, like 100 megawatts, and so this would be the like pumped hydro. You're pumping the water uphill and so on. It's a very slow process, and then the rapid response would be those flywheels. Storing energy for hours instead of tens of hours. Let's look at some of the interesting battery designs that they have. These are flow cells or fuel cells or flow batteries. And so this one is interesting. You've got this reaction going on. Let's see. So on the sulfur side of things, you've got this reaction, and noticing it's producing sodium ions. And over here on the bromine side, it's consuming sodium ions. And so sodium ions are moving from the left to the right or right to the left, depending on if you're charging it or discharging it. So if you're discharging it, you're running this backwards. If you're charging it, you're running it forwards. And so this right here is the current limiting step, this ion selective membrane. And so however many amps you want out of this system is how fast you can get sodium to go across that barrier. Electricity is not our limiting factor. We can push electrons incredibly fast. It's how fast can we conduct ions. And so we can use these pumps to pump these electrolytes around, and the reaction takes place at this membrane and generates the positive and negative charges, and we can put that on the source or the load. So when it's a source, we're charging this up and we're pushing the sodium ions to the left. And when it's drawing current, then the sodium ions are going to the right, and we're able to generate electricity. And here's this is a 15 megawatt facility, so it can generate 15 megawatts. And here's your large basins here. Here's an interesting one. This uses vanadium in the negative side and vanadium in the positive side. And so once again, we'll be conducting electricity using electrons, but also pumping these vanadium ions back and forth. This battery can be as high as 85%. So I just went through sort of a survey of all of the different kinds of flow cells I could find. So this vanadium cell storage has been applied at several commercial sites. As of 2008, they had about 8,600 megawatt hours stored in those. So that's a pretty good flow cell at 85% efficiency. Here's a zinc bromide cell. This one's pretty cool. It's been containerized, so it can be delivered in a container, set up, filled with its reactants and powered up. Again, these are not just electrical generators, but they're electrical storage. So you could set this next to a power source like a windmill or a solar cell, and you could charge it up and then use it when the wind's not blowing or when the light's not on. Okay, net efficiency is about 75%. Once again, that means you put 100 joules into it, you can get 75 joules out. Lead acid batteries, we know those from automobiles. You can use those to charge up and discharge. So you could make, again, next to a wind farm, you could put this in so that you could draw off the battery warehouse whenever the wind's not blowing. This is a 10 megawatt facility. So just look at the footprint. That's a lot of lead acid batteries. You see here, there's a lot of sulfuric acid. And we're charging that up. That's potentially a lot of hydrogen gas that can come out too. So anyway, that's why they're monitoring it. That's why he's walking around. Yeah, so this is a pretty decent footprint, and I would say only 10 megawatts. I mean, 10 million watts sounds like a lot, but we'll see in a second. We'll compare that to something. I think that's just the facility. Yeah, I mean, there's definitely vents on the batteries, and they probably, oh yeah, these guys right here may be, yeah, this may be like a little bit of a vent hood action going on so hydrogen doesn't build up. Yeah. So this one I call the fire and brimstone battery, because I cannot imagine what this would look like if if air got in. So this got molten sodium, which reacts with air, and especially humid air, to generate hydrogen gas and sparks. So that's not good. And then sulfur, which will burn in air too. And that's incredibly toxic when it burns in air. Okay, it'll kill you. Okay, so here we have this, and then we have this aluminum tube where the sodium ions go through. So once again, we're conducting sodium ions. That's the current limiting step. But I mean, they've got this technology. This is a 2 megawatt battery installation next to a wind farm. There's 17 of these set up, and then this warehouse next to it, I guess, to contain some of the generator equipment. So they've put this, and it's got a nice efficiency, almost 90%. So that's really good. It's a scary chemical reaction, okay, and scary reactants, but molten sulfur and molten sodium. So if this get hit by a car or a tornado, it would be a mess. But we'll see. And then lithium-ion batteries. Here's sort of a lab-based lithium-ion cell. We use these in our laptops. Now they make these nice little batteries. I can't remember the number, 16385s or whatever. There's sort of a standard cell now for these lithium-ion batteries. They're about 1.5 times longer than a AA, and a little bit wider around. And that's the standard cell now for all your laptop batteries and everything. And Thomas and I, for a while there, were pulling these out of laptops. Like you have a junker laptop, the battery's dead. Typically, it's one of those cells out of 15 cells that have gone bad. And so you pull it out and you test all of the ones, and you get the other 10 that are still good, and you can make yourself like a phone charger. And so the problem is trying to weld them together. And so in order to provide, like a 10-hour phone charger, you've got to weld these leads together and put them into parallel with each other. So he got on YouTube and started looking up how to do this. And you can make a spot welder with a car battery. Okay, you just need to buy this one automotive solenoid, and you need something that will pulse that solenoid for a programmable amount of time, like just 100 milliseconds. And so he has a Raspberry Pi that can send that signal to the solenoid. And so he made a little spot welder. You got a couple of copper wires here, hooked straight into a car battery. Okay. And then a little solenoid here that's computer programmable. And then he has a foot pedal here. And so you can step on the foot pedal, and you put the copper wires right on that nickel strip and step on the foot pedal, and it goes pow. And that current running through that nickel strip is enough to weld it to the top of the battery. And yet you don't heat up the battery and cause it to break down. Yeah.
So, it's electronics. You can't just solder it?
No, because the heat, it's too slow. The nickel strips conduct the heat away so fast, and so then the whole thing has to heat up, and so it damages the battery, and so it's a damage problem. Yeah. And so if you could spot weld it, you could do it very quickly, an intense amount of heat, but in a small spot. Yeah. And so that's what he was reading about. He thought about soldering it, but online they were saying, no, you really have to spot weld these things. And so we made several 12-volt battery packs from old laptop batteries that you could plug into the car or whatever and charge them up, and then you could plug your phone into those, and you just use a car charger to charge your phone. And so it's taking it. So we just made some nice little 12-volt. They look pretty scary. This looks like a little, how you make the dynamite and the little pattern, it's like those, and he's welded them together like that. And then he coated the whole thing in black electrical tape because it's real cheap at Harbor Freight. We're like, coated the whole thing. It totally looks like a bomb. I mean, so it's pretty fun. And then there's the metal air batteries, which some of these metal air batteries you're used to. These are the little button cells too. And so they'll have a membrane in there where air can get in, and oxygen is one of the reactants. But for the highest current that you can get, you have these ultracapacitors or supercapacitors. And so they have an electrolyte. Again, you can charge these up, and they deliver an enormous amount of current. So, in, say, an automobile, you have the battery for the storage of a large amount of energy, and then you have in line with that some of these capacitors, so that when you hit the when you hit the accelerator, then it can dump this extra current into those motors and give you a lot of torque so that you can get going. But then they run out of electricity. But now you're not needing to pull as much electricity as fast. You don't need the current that you need to get it started, and then the batteries can deliver that current. So it's about impedance. These have incredibly low impedance. So if you want to go from a dead stop to moving a large amount of mass, like a vehicle, you need a lot of current through those coils. This is what's dangerous if you hold a motor still and you turn it on, like a ceiling fan. If something's messed up with the ceiling fan and you flip the switch and it just goes, but it's not moving. It's trying to get that thing moving, and it's putting a lot of current into those coils, and they will heat up and can catch fire. Okay, so anytime I hear that noise, that 60 hertz noise into an electrical device, and it's not doing what it's supposed to do, you're putting a lot of current, and then it will flip the breaker if it's too high. But it is the danger of it not being high enough to flip the breaker, but high enough to generate an enormous amount of heat in a device that's not supposed to be like a heater, right? And if you got a space heater, it's pulling a lot of current, producing a lot of heat, but it's made to do that. It's got fans, it's blowing the heat into the room. The ceiling fan's not made to do that in the motor housing. And so I always kind of panic when I hear that. Okay, here's the compressed air energy storage, again for load leveling. And it does kind of look like that water hammer. You've got the electricity going, on the grid, but then if demand changes, then you compress that air and stick that air down into a limestone cavern, say, and you pump that air pressure way up. It's not going to be any problem. The geology can handle it. And then when demand increases again, you bring that air back out, run it through the turbine, and generate electricity with it. These are getting up to commodity-sized storages, so and power. So 290 megawatts versus like those battery and flow cells were in the tens of megawatts. So now we're at least in the hundreds of megawatts. So this is more like a power plant than batteries. Okay. And look here, this is the largest one. It says 2,700 megawatts. So that's planned for construction in Northern Ohio. We need to go see if that's been opened. And then pumped hydro. They're saying that there's over 90 gigawatts of pumped, so 90,000 megawatts of pump storage in operation worldwide. Who knew, right? And you wouldn't know. You're driving along the highway, you see this nice little hydroelectric dam, okay, generating electricity from the river. And then up on top of the hill is this reservoir that nobody ever sees, right? Now, again, this is going to be lossy. They're going to get evaporation, and so they need to put a membrane on that, or put those little beads up there, evaporation beads. So this is in Pennsylvania. And here's that flywheel storage. Is a little bit more of a picture of it. And so these are up to 90% efficient. So that's fantastic. I really like that. So here's all of this chart shows all of the different things that we've talked about. And we really have these two categories: energy storage versus power storage. Power storage would be what I'm talking about, like short bursts of power, so high current. And then energy would be commodity levels, like the compressed air, storage, pumped hydro, these flow batteries, and then getting into the sodium sulfur battery, the fire and brimstone battery. It's in that mid-range. It kind of makes that branch from energy applications over to power applications. And then you get down here to flywheels and ultracapacitors. Those are your high torque items. And lead acid batteries, obviously. You could run, the earliest electric vehicles were on lead acid batteries. And they worked okay, but the lead was so heavy. You're really working against yourself. And so that's why the lithium-ion battery has been such a revolution, because it's so lightweight. Flywheels don't work in terms of automobile or things that move. Okay. Did y'all ever do the physics demonstration about angular momentum? And they have a guy sitting on the stool and the bicycle wheel? You ever see that? Okay, you see, what do? They like spin up the bicycle wheel and give it to the person, and he's holding it, and then he tries to turn it. Yeah, and so when he tries to change the angular momentum, it puts angular momentum on him, and he's in a spinny chair. And so he turns it, and then he starts to spin. Okay, and he turns it the other way, he starts to spin the other way. Okay, and so whenever you have something spinning, you have an enormous amount of angular momentum. That's how you can balance a bicycle. Right? Sit on a bike while it's not moving, it's very hard to balance. But once you get those wheels moving, that angular momentum vector, it doesn't want to change. And so then your bicycle is balanceable. Well, if you think about coming to a stoplight and you hit the brakes and you take all of your momentum and you stuff it into a flywheel, okay? And so then now that flywheel is spinning and stored all that energy. And then you hit the gas and you want to turn the vehicle. Okay, if you turn one way, it'll help you turn, and you'll really steer quickly. And if you turn the other way, it'll fight you, and you're trying to turn, and you can't quite turn the vehicle because you're changing the angular momentum vectors. And so that's so flywheels and motion don't work well together. So these would be for storing things at your house, not necessarily in a vehicle. Now, here's the solar steam. So we could take the sun and shine it on water, make it go to steam, and then run that through a generator and generate electricity. And so look at the footprint of this thing. And so all of these parabolic reflectors are focused on pipes that have water in them or steam and make it hotter. And then they have the generator over here to make the electricity. And so this is 354 megawatts of capacity. But I looked at this road, and I used this road sort of as a scale. And that's about the same as this road right here. And these are the 3 coal-fired units at Fayette County in LaGrange, Texas. And look at the footprint for 590 megawatts. So these are about the same scale. So I could put this whole power plant here, probably right there. And so even though, yes, we can make power with steam, look at the footprint that we have. And this is out in the middle of nowhere in California, because you need such a large footprint of land, and you got to buy cheap land to do that. You can't buy this, put this in downtown. Yes?
And I mean, the steam is great, but you have to make the steam.
Yeah.
Which comes from fossil fuels.
Well, this would be making steam straight from the sun.
Oh,
yeah,
right.
so that's
natural gas turbines.
Yeah, and so this right here, this is all using the sun to make the steam, which sounds great. It's got a big footprint. And look, I'm just comparing the footprint to these 3 coal-fired power plants, which are all about 500 megawatts each, and this is 340 megawatts for this one. But it's not really fair to compare the footprint of coal without taking into account where the coal is mined. Okay, here's a photovoltaic installation in Germany, and this huge, look how huge that thing is, and it only generates 40 megawatts. Yeah, it will improve as solar improves, but still. And then this is the coal footprint. I just saw that this is the most efficient explosion I've ever seen. Okay, so check this out. That's a beautiful use of explosives. You know what? Yeah, you see what happened there? So this is a coal seam, and they're just unzipping it with explosives, and then they come in with the trucks. And so that's all you pretty much have to do to get coal. That's why it's so cheap. You just take the topsoil off and put in some ammonium nitrate fuel oil and then unzip it, basically. So that coal has a huge footprint, but it's in Wyoming and other places where that was in Powder Basin. Okay, let's talk quickly about the efficiencies of of solar panels. This is the National Renewable Energy Laboratory, and it's fantastic to go there. You can type in your house parameters, and like I typed in 1000 Sam Houston Avenue, Huntsville, Texas, for the university. And for a 25-meter array, so 300 square feet array, we could generate 5,000 kilowatt hours a year. Okay, and the value on our particular grid would be about $500. And so here's our output that we would get, and how much energy we would get each month, and so on. And these are the conversions that I said to use for calculating the cost of solar energy. So $8 a watt and 10 watts per square foot. Now, when I was showing this to Thomas, because we got into a discussion about this, he goes, "Oh, those numbers are terrible. We'll still use these for the homework, but things have improved a lot." So this is Thomas's research. He went out and looked online for all different kinds of sources of solar panels that you could buy, and here's their price and their square foot and so on. So he did the price per watt and the watt per square foot. So we're now getting, instead of 10 watts per square foot, we're getting about 15 watts per square foot. That's fantastic. And then instead of $8 a square foot or a watt, it was $100.50 a watt. Now that's buying this panel. That's not installation. Okay. So when you go to installation, then you end up with the installation cost. And so, yeah, in 2010, the number was close to $8. Now it's down to around $270 for residential. So that's pretty good. Yeah, and so that's less than half. And so these numbers that I calculated for $24,000 for a home is now $12,000, and that's getting into the range that people could go ahead and start putting solar panels on their house and actually pay them off in a reasonable amount of time. You want the payoff of the money you save to pay the materials off and the installation before the devices break. So if the lifetime of the device is 8 years and it takes 9 years to pay it off, that's not smart. Okay. But if the device is 10 years and it takes 5 years to pay it off, now we're talking about something that you're going to gain from. So solar is on its way, and I'm pretty big on solar. And then this is just an exotic form of energy. Some things are just naturally hot, like radioactive substances. This is plutonium-238 purified, and look at that. That's not painted. That is red hot. Yeah, can you imagine that thing falling out on your foot, But anyway, this is a power supply for a satellite because this is going to last for thousands of years. And so they use these what are called Peltier cells to generate voltage from heat differences. So that's radiothermal battery, or the thermal electric effect. And you just have this device that if you put a voltage on it, you can pump heat from one side to the other side. And if you have heat going from one side to the other side, it'll generate a voltage. And these are how the plug-in, some of these plug-in ice chests work. You plug it in one way and it makes the ice chest cold. You plug it in a different way and it makes it warm. Okay. It's not very efficient though. It uses quite a bit of current and doesn't really push that much heat. Okay. But for low power applications, for long periods of time, they can send these out into space. Their battery lasts for thousands of years. Yeah. Or you put them in the middle of Siberia to have a temperature monitoring station, a weather monitoring station. And Russia did that. They used radiothermal batteries and put them in Siberia in the middle of nowhere, and then just generate data for them. Nobody has to maintain anything. There's no battery that's going to run out. And those are the scariest things now because they don't know where they are. And so you've got some of these old weather stations with radiothermal batteries that have a ton of radioactive elements in them, and some of them are missing. So that's one of the things that I worry about also with dirty bombs, is that some of these radiothermal batteries have gone missing. And so we don't know where they are. Yeah.
Like the Russian nukes, huh?
Yeah, that's right. Yeah. And then the one other area that's crazy to think about is we've never tried to harness. I think we maybe tried, but there's a lot of electricity in lightning. And the good old, Ben Franklin, he found that. This is a video of a plane getting struck by lightning. It's pretty cool. All right. So be thinking about all these topics, and when we get to Monday, we can chase the rabbits that you want to chase.